Everybody, we're going to learn about memorization of novel examples in this video. So how do deep learning models memorize information? Well, they memorize repeated examples, that's in the last video, and they also memorize really novel examples. So here's an example that has been proven to be memorized, maybe not this exact image, but an image of a white peacock. Why is a white peacock interesting enough to memorize? Well, it's pretty rare. Normally we have the colorful peacocks. And so if the goal is to score well on the test data set, and a white peacock might show up in the test data set, then the model will optimize to score well on this during training. And to do so, because it is so rare and infrequent, it will become memorized. So let's explore how we can reason about this. How might we actually try to find these? Well, there's an idea of leave one out. So it happens a lot in privacy that we try to figure out if we leave one out or if we put one extra in, do we change the behavior of the system or the model? Because if it's just one example and it makes a huge difference, then we can infer a lot of things about that example. And so it's a huge violation of privacy. When we take leave one out training, what we do is we take our training data set here that we might have pre-built, and then we're going to take one of them and we're going to pull it out. And we're going to train a model with this. So this is going to be model without. And then we're going to train a model with all of them. Could have drawn it the other way around. And we're going to take the performance of the model without and compare it to the performance of the model with. And this difference between these two models is going to show us how much memorization is happening. It's also going to kind of show us, in a way, we can start to think about it as how memorized the example is, and we can think of it as how little privacy does this example have, if we can see such a difference between these models. And Vitaly Feldman actually proved this out theoretically, and then several people after him proved out for all different types of models and distributions that basically we have our model error. Remember, we're trying to make this as small as possible. And then we have our optimal model, right? This would be the most perfectest model of all. We usually don't get there because it would probably be based on optimal data and optimal computation, which we don't always have. And then that optimal model score plus some sort of normalized penalty. And it's normalized based on some properties of the data set and properties of the task. But this is a penalty for not fitting the long tail in the case of that we're looking at with Feldman's paper, although now it's been proven out for a few other distributions. But with this long tail, remember, we have something like this, and this is a vast majority of the distribution. And yet, if we're training on this, which we certainly are, maybe we're even oversampling on this, so we're training on it a lot, we are definitely going to memorize it, because the error in this tail is going to be a lot more than the error over here because of the properties of how the learning happens, which you learned a little bit about in the previous articles. And so Zhang and Feldman got together. So after Feldman had written that paper, Qiwan Zhang, who's done a bunch of amazing work in memorization, got together and they started to try to apply basically this leave one out method and to find, okay, it happens theoretically, but does it happen in practice? And that's when they found this kind of swing example that I know that you saw previously. So on the left, we have the training example, and that is a person on a swing. And then when we take this out, when the model doesn't see it, it scores very poorly on this test example, which we can see is literally the same photo shoot on the same day with the same person. And that isn't the only example they found. In fact, you can look through many, many examples that they had. They have ones, here's just a few, where you can see, again, the resemblance between the training example and the test example that, again, had a significant difference if it was not in the data set. So again, these are all memorized examples that are happening in these large-scale deep learning models. And you might be like, well, these are just, normal public images, public data sets. What's the big deal? Well, you might have heard about diffusion models. You probably used a diffusion model. And if you've ever used a generative image where you put a prompt in and you create an image, you've most likely used a diffusion model. So Dolly is a diffusion model, Flux and all those things are diffusion models. So with a diffusion model, we take noisy randomness and a prompt, and then we try to output image that best represents the prompt over time. And in the process, we're getting kind of less noisy each time until we get to some sort of end point. And this basically, you can think of this as iterative noise reduction towards whatever this prompt means for the model. Now, what does the prompt mean? Can the prompt be memorized? Well, unfortunately, yes, the prompt can be memorized. So here's an example that was extracted from a diffusion model by a group of researchers who were able to train a big diffusion model, the same as the stable diffusion when it first came out. This training set example of this author's face was seen only 2 to 3 times in the training data set, and yet if you put in the person's name, you could very much reproduce the training set image. And that's not the only example. You might have used some sort of photo editing tools. There's this property called inpainting, which allows you to kind of remove a piece of an image and say, hey, can you please generate the rest of this image? Well, we have here the training data. We have the gray here is the inpainting, so the mask, so to speak. And then on this side, we see the example if it was in training. And on this side, we see the example if it was left out. And so we can see here again, reproducing the leave one out with diffusion models. It is quite obvious that diffusion models memorize training data. And this has been proven time and time again. So diffusion models, compared to many other models, memorize quite a bit of training data. But they're not alone. So does ChatGPT. So you might have seen this poem attack where a group of researchers, again, I think this is Nasser et al., were working on measuring actually extractable training data from open and closed LLMs. And they were able to devise this type of attack, which I like to call the poem attack. And we're basically able to find sets of tokens. Poem is a token in ChatGPT tokenizer. So sets of tokens that they could get the model to repeat and then spit out memorized information. So here we can see the memorized information is personal data of a person, most likely scraped from their website, but certainly not expected to be memorized and reproduced by a ChatGPT model. Why does this attack work? This attack works because it probably unlocks the ability to interact with the base language model. So when we train LLMs, we have 2 training steps. We have pre-training, that trains a base language model, as we call it. And then there's usually fine-tuning with usually these types of instruction or chat prompts. And this changes some of the behavior, obviously, of the base language model. But if we had access to the base language model, we could probably find a lot more of these types of memorization. And yet very few companies release their base language models. And if so, they release a very sanitized version usually of the base language model. And so this is a real problem in actually measuring memorization during the training. And what this produces, or what they were able to find in looking at ChatGPT versus many of the other models, is ChatGPT actually memorized quite a bit more of what they were able to extract than the other models. And so I'd like to just point out, ChatGPT has had a huge amount of money put into it to create supposedly one of the best guardrailed models. And yet they were able to extract many more memorized series of tokens, memorized text from ChatGPT. And they only spent I think $200 on extraction attempts. But if they had spent, 3-4 times that much, they predicted they would be able to extract more than 1 million text examples that were memorized from the original training data set. If we had access to the base models, we could actually show a lot more of what's able to be extracted. So here's an example of a model inversion attack that I wrote about in my book, Practical Data Privacy. And these model inversion attacks basically can take a target class. Here was a facial recognition model. So the target class, or you can think of it as the target prompt if you want to, was this person's face on the right. And basically doing iterative investigation of the model itself, I was able, with only my personal computer, to extract the model on the left after about 10 minutes. And so we can see here that if we were able to get access to the models, we can show that this memorization is happening. We can extract examples of that information, and we can find examples where PII is memorized, and we can find examples maybe where it's harmless memorization, where it's a Peacock and we should memorize it. So what we can see with all of these examples is that extraction of personal data, despite guardrails, despite closed and paid API, is both theoretically and practically possible. Without giving access to the pre-trained models or the models themselves, it's going to be difficult, if not impossible, to actually reasonably measure the amount of extraction that we can perform, or reasonably measure the amount of memorization in these models. I'd love to hear your opinions. What should we do about this memorization problem? Do you think it's okay that we memorize them, or should we do something essentially to intervene with this problem? Thanks for your attention, and I look forward to your comments.